Hey guys, this is 4.3, right? So this is all about acids, and you'd be surprised how much I can talk about acids, but I'll make this quick since you already know quite a bit about acids. So it says substances that increase the concentration of H plus when dissolved in water. This is what the Arrhenius definition is. It's like the simplest definition there is, and it looks kind of like this. So we have HCl here, and when it breaks up into, or dissolves in water, it breaks up into H plus and Cl minus. Okay, HCl is an acid because the higher the concentration of this compound, HCl, when it dissolves in water, the higher the concentration of the H plus, and that's what makes it an acid. Okay, so we can talk about the Bronsted-Lowry is like a more inclusive definition of acids. So if I have like the Arrhenius, if we're talking about like Venn diagrams, and I have the Arrhenius definition of acid, Bronsted-Lowry would be like including the Arrhenius definition and also including other things. It says it's a proton donor, which means that the proton is, of course, the H plus, but there are other substances that will increase the H plus concentration without actually having the H plus in the actual formula. And Bronsted-Lowry includes those substances as also acids. And I don't want to get into that because we don't need to, so I'm going to keep pushing forward here. What we're concerned about is if it has an H in front, then we consider it to be an acid. Now, it doesn't necessarily have to be a strong acid like HCl. We know that HCl breaks up into H plus and Cl minus 100% of the time, which is why it's a strong acid. And that does not happen for other things. So let's keep going here. There are only 7 strong acids. I talked about these before. If you did not write them down for 4.1 and 4.2, then I want you to get them right now. Please take a minute, pause this, and write them all down because it's very important that you know which ones are strong, because then everything else is weak. And that's really the reason why. So you recognize it as being a strong acid so that you can recognize those things that are weak acids. And that'll be more important later on. Substances that increase the concentration of OH when dissolved in water. And for Bronsted-Lowry, that's a proton acceptor. Now, I'm not even going to talk about Bronsted-Lowry for proton acceptor, but we will get into, like, obviously, concentration of OH. We may talk a little bit, but not too much about pH and what that actually means, but that is all about the H plus concentration, and I'll talk more about that later, possibly. So strong bases are those of soluble salts of hydroxide ion. As it turns out, there's not many of them. There are 5 for the alkali metals. We talked about that already. I gave you that list, so this is going to be real short. Remember, we talked about lithium, sodium, potassium, rubidium, and cesium. Those are the 5 in the first group that are all strong bases. So LiOH is a strong base. Consequently, these 3 then, and the second group at the bottom, so calcium, strontium, and barium also make, what does it mean to be a strong base? It means exactly the same thing. It does to be a strong acid. It means that this separates into Ba with a +2 plus 2 OHs like that, and this happens then 100% of the time. So that means that it's always happening like that. They're always separating. Okay, so acid-base reactions, guys, I'm telling you, this is exactly the same thing that we had before. This is a double displacement reaction, just like the metathesis reaction is a double displacement reaction. So in an acid-base reaction, the acid donates a proton to the base. What they make then typically is, if it's a strong acid, strong base reaction, then it comes away looking like something plus water. You would know this because this was how we talked about it for sheet number 7. So this is still a double displacement reaction where I have on the other side here A and D coming together and C and B. Now C and B would look more like this, where the C is the H and the B is the OH. And that's why I write it that way, so you can see them separated. Nothing is different. This is still a double displacement reaction. There is nothing different about this. We end up with water. But when we apply, here's the one extra part to this. When we apply the ionization or the ionic equation, take a look what happens for any strong acid, strong base. So when a strong acid reacts with a strong base, the net ionic equation is, now check this out, these things that are like this all break apart. This one doesn't, of course, because it's a liquid, which means that I have Cl here and Cl here not changing, so I can get rid of them. Okay, Na here and Na here not changing, so I can get rid of them. This is how you do a net ionic equation. Notice what I'm left with then is simply an H plus OH minus yields H2O like this, and that is the net ionic equation for every strong acid, strong base reaction. Okay, they all look exactly the same. It's H plus OH minus yields water. That's it. Strong acid, strong base, always the same. Okay, so this goes into explain just what I did explain, so I'm going to go. This used to be some type of like graphic that shows you that the milk of magnesia changes into the magnesium. So we got this plus this, right? And on the other side then you'd get magnesium chloride plus water, and magnesium chloride is clear, which is why, is clear, which is why when you pour the acid in the milk of magnesia, you can see what's happening down here is that you're forming magnesium chloride, which has no color when it's dissolved in water, and and that's why the milk seems to go away. It's not actually milk, it's just a cloudy, doesn't matter. All right, let's move on. So gas forming, gas forming reactions. These are exchange reactions that we see. Notice it's still like we're starting off. Now here's the difference though. Notice that when we have certain types of polyatomic ions over here, they actually then break up into something like this, where you can see gas and water. So we produce water and then we produce a gas, and all it's doing, in case you haven't seen this before, carbonate is CO3 with a -2, but on the other side here, notice that the carbonate then gives up an oxygen to water, right? And once it does that, then it produces carbon dioxide. You guys know what carbon dioxide is. You've seen that many times. So there are certain situations where we produce water. SO3 does exactly the same thing. It even has the same charge, SO3 with a -2. On the other side, SO2, and then an oxygen goes to water like this. You don't have to memorize this. You don't have to do this. I'm just showing you because this is another pattern for double displacement reactions that I didn't teach you in Chapter 3, but it still works very similar. All right, let's move on here. So they talk about this. You don't want to do this one in class because of this nasty little molecule right here. This is the rotten eggs molecule. So hydrogen sulfide literally smells like rotten eggs wrapped in a fart. It's awful. Okay, moving on. Oxidation reduction, I believe, is the beginning of 4.4, so we're going to stop there. Much shorter screencast this time.